Now we want to start up on the last kind of big idea within chapter 12 and in reaction kinetics, and that is the idea of mechanisms. So far, we've looked at laws, we've looked at the rate laws, integrated rate laws, allow us to make predictions about actual experimental results. How fast will a rate go? How will concentration change over time? We can understand how to control reaction rate using collision theory. We can make predictions as to how to increase rate based on things like surface area or on temperature. And so, we can kind of put those together, and the rate law, we know, has these parts, the K and the orders, and collision theory really helps us explain that K. That's where all that comes in. And so we've gotten a nice kind of description. So what we want to move forward now is, where do the orders come from? We know that the orders, we've seen places where the orders don't come from, but otherwise it's just been a result of describing experimental results. So can we explain them at an atomic or molecular level? So let's look at some cases, like for example, the reaction NO2 plus CO becomes NO plus CO2. If you do this experiment at certain temperatures, you find that the rate is equal to K times the concentration of NO2 squared. Okay, and so that would mean that NO2 is second order. CO doesn't show up in the rate equation, so CO is 0th order. All right. But if we think about collision theory, we said that NO2 plus CO2, we'd have collisions of that. And so if there's collisions of CO, that would mean that the order of CO would matter, right? If you increase the concentration of CO, there will be more collisions that involve these CO molecules. But the order is 0, meaning that the rate doesn't increase when you add more carbon monoxide to your mixture. So there's something going on between this idea of collisions that we've talked about that underlie reactions and these overall reactions that we're talking about, and somehow orders fit into this. So where do these orders come from? In order to answer that, we need to talk about the idea of a reaction mechanism. So when we write an overall reaction, we are writing the overall change that we're seeing. But that reaction occurs via multiple consecutive elementary steps. So an elementary step is a chemical equation involving a single molecular collision. When I say a single molecular collision, I mean an event, a single reactive event of one molecule changing or two molecules colliding. Normally an elementary step is pretty small changes. Usually only one or two chemical bonds are broken. So for example, if we look at the combustion of ethane, 2C2H6 plus 7O2 becomes 4CO2 and 6H2O. When we're writing this overall reaction, we're describing a change of 2 C2H6 molecules and 7 O2 molecules. This does not happen via a single collision of 2 ethane and 7 oxygen molecules. That's just not going to happen where you'd have 9 molecules involved. Instead, there's going to be numerous consecutive small changes. If you look overall, this is just a kind of a pictorial representation where we have our 2 C2H6 and everything else is our O2 molecules. If we just look at overall between all these molecules, if we're going to react, we would have 21 bonds would have to break. All the oxygen-oxygen bonds, they would have to break. We'd also have to be breaking all of these carbon-hydrogen bonds. The carbon-carbon bonds would have to break. And then you form 20 new bonds, 8 of which are double bonds. So this is a pretty massive rearrangement. There's a lot of bonds that are breaking at a single time. It is very unlikely that that would happen via a single collision. You could maybe think up one, but the activation energy would be astronomical. And so, and the sterics would be crazy in terms of how those atoms would all have to line up. That's just not going to happen. So a reaction mechanism is the sequence of elementary steps that combine to give you an overall reaction, right? You're going to say, here are the small changes that overall combine to give you your big overall reaction, the overall change that you've written down. So when you're doing experiments and looking at reaction mechanisms and kind of this idea, these reaction mechanisms function as a theory. You cannot prove a reaction mechanism. You theorize a reaction mechanism. This is what you think is going on. This is the sequence of steps. And your experimental results can support those changes or those steps, but you can't prove it. You can disprove a mechanism, but you can't prove a mechanism. So what's an example of a mechanism? Well, we'll look at the conversion of ozone to oxygen. So O3 is an ozone molecule. O2 is an oxygen molecule. So our balanced equation would be 2 O3 molecules becoming 3 O2 molecules. Okay. If we are looking at overall, what we would have to do, we'd have to say break this bond, and form a new bond between those two oxygen atoms. So that's not too crazy of a change, but even that's still a lot. It is unlikely that you will break two bonds and form a new bond all in one collision. It's really high energy requirements. You'd be breaking two bonds. And you also would have some steric issues. What is the kind of orientation that these molecules have to collide in just the right perfect way? It's just really, really unlikely to happen via a single collision. So instead, it's going to happen via multiple steps. So we're going to break these down into steps. The steps that we could propose is that we would get decomposition of one O3 molecule after absorbing some ultraviolet light. So some light comes in, it collides with the O3 molecule, and then that molecule, one of its bonds breaks, and you get an O2 molecule and an O atom. Okay, so we make an O atom. This is a new species that's around. And so this is there. And so now this is present, and this O atom can then react with something else. So these molecules will leave because they're products of the first elementary reaction. That O atom could then go find an ozone molecule, and now you would be breaking one bond while forming one bond, and that is much more likely to occur, and you end up with some O2 molecules. Okay, so this is the idea where we have these kind of sequential ideas. Instead of a single reaction event, there are two reaction events that have to occur in sequence. They have to occur in sequence because you need this O atom that was created in the first process to be used as a reactant in the second process. So this idea of having these elementary steps combined to give an overall reaction is something we want to work through. Let's see what it means to combine elementary steps into an overall reaction.
So when we want to combine reactions, basically what we can think about is we're going to add them together. And what that means is basically we take the arrow, and that stays in relatively the same place. So our reactants, what we do is we combine all of the reactants from all of the equations together. So we have the O3, the O, and the O, that becomes O3 from the top reaction plus the O atom plus O3. So we keep all of those together. And then over here I have the O2 plus O, O2 plus O2. So I'm going to keep all of those together. O2 plus O plus O2 plus O2. And so now that I've got everything combined, what I want to do is I want to go through and find things that are basically the same. And so one of the things I can see is that I have O3 plus O atom plus O3, O2 plus O atom plus O2. So I can see that O atom shows up on both sides of the equation. I don't want that. With chemical reactions, we want to be showing change. So I want to simplify, cancel out anywhere that I see the same thing on both sides of the equation. At the same time, or let's write out what we got now. So we'll cancel that out. So I got O3 plus O3 becomes O2 plus O2 plus O2. So we don't have anything that's showing up on both sides of the equation, but what we do have is we have some redundant things. We have O3 and O3, O2, O2, O2. So with elementary steps, we normally write out multiples of a given molecule, but we don't want to do that when we're talking about overall reactions. We want to combine them together. O3 plus O3 can be written as 2O3. O2 plus O2 plus O2 can be written as 3O2, where we just have the number of molecules as opposed to writing them all out. So when we're combining reactions like this, we're adding combining steps. What we're really showing is what the overall effect is. If you have an O3 molecule and it reacts to this happens and then this reaction happens, those two steps in sequence overall accomplishes the change of two O3 molecules becoming three O2 molecules.
In this process of obtaining an overall reaction, right? So we can take the steps and see that they combine the overall reaction. This is the first test of whether or not a reaction mechanism is realistic. And this idea of support or disprove. Does it actually do those sequence of steps actually yield the overall reaction that you want? So that's your first test. A reaction mechanism has to correspond to the overall reaction. One of the other things about a reaction mechanism, there are these steps, is that they indicate what the intermediates are. So this O atom that is created in the first step is then used in the second step. And so this idea of that it's something that's created and then is used, this is called an intermediate. It is something that's a part of the mechanism, but not the overall reaction. So you'll note the overall reaction is ozone becoming O2, not O atom. And so these intermediates are substances or some sort of molecule atom that are created in the process of going through the steps. Oftentimes intermediates are reactive. They're not unstable, because unstable means falls apart spontaneously. O atoms are stable. They don't just fall apart. The electrons don't just leave. The protons don't just leave. They're very reactive, and they want to do more chemistry, but they don't spontaneously fall apart. It's very quick to react with, say, this other ozone molecule in the second step, but they are stable, just highly reactive.
Participation 918, question 1. Consider the following reaction mechanism. Step 1, A plus B goes to C. Step 2, C plus B goes to D. A, what is the overall reaction? B, what intermediates are involved in the mechanism? This is the first question on participation 918 due Friday, September 18th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, consider the following reaction mechanism, this one right here. What is the overall reaction and what intermediates are involved in the mechanism?
So when we take this idea of having these sequential steps, each of these elementary reactions is a collision. And so these are the processes that have an activation energy. Okay, and so the activation energy of each step is going to be unique. Sometimes maybe your first step has a really high barrier, like we can see here. This first barrier is really high, and then the second barrier is not so much. One thing to note, the second barrier is measured relative to the intermediate, because that's the intermediate is what exists. And that intermediate is what's doing the reaction, right? That's what's doing the second reaction. So that's where the barrier is measured relative to. So, or you can also have situations where the first step's pretty, short barrier. It's easy to get over that, but the second step is quite a high barrier. And so we could have 2, 3, 4, 5, 6 steps that make up our overall reaction. When it comes to reaction mechanisms, you're really only limited by your imagination in terms of coming up with them. So far, if you have a reaction mechanism, you have all these different bonds changing, all these small elementary steps or whatever you're doing, and as long as that combines, all of those steps combines to give you the overall change that you're talking about, that's potentially a valid mechanism for now. And so, you have all these potentially valid mechanisms that you could potentially be working through. But, the thing is as far as chemistry happens, the reaction's actually going to happen by whatever the easiest path is. So you can imagine I'm going to take these ozone molecules and they're going to collide via a single collision. We're going to go to the transition state where all of the bonds are broken. I'm going to break the bonds. They're going to become all a bunch of isolated atoms. This would be a really high barrier because you're breaking a lot of bonds. When it comes down to these activation barriers, it's really just breaking bonds, right? You're breaking bonds to form new ones, but you got to break those first. And that would be a really high barrier. And so functionally, the reaction will not happen in this way. Atoms don't care about your imagination. They're going to follow the actual reaction mechanism that has the lowest energy, the easiest sterics, the least restrictive sterics, the simplest changes, while a lot of small changes are more likely than one big change when it comes to reaction mechanisms. So in the case of ozone, you have the light come in, you break one bond. It's going to be a smaller barrier. You do create this oxygen atom, which is an intermediate. And that oxygen atom is highly reactive. But it's important to note it's not unstable. It doesn't fall apart. That's why there's this little kind of well here, this little bottom. That is a stable thing where you have this isolated oxygen atom. Now you'll note this barrier for the second step is very short. It's very low to go up above this second hill. That's a tendency for intermediates. Those secondary reactions tend to go pretty quickly. And that's how this actually works. So it's much more likely that you get a lot of small steps. You have all these small steps. Overall, they have short barriers or small barriers that are easier to overcome. And you make a lot of little changes that overall leads to a big change among your molecules. With these ideas of mechanisms in mind, we can return to the idea of propane combustion. So we said this doesn't happen in air conditions when you have C3H8 and O2 because there's a huge barrier to collision. You have 6 molecules that would be potentially colliding, and that's just not gonna happen. You need to have a lot of elementary steps here. So there's a lot of steps that you need to get through in order to have this reaction occur. So we know that we said you have this flame, you can kind of get it kick started. But what really happens is that flame reacts with the C3H8 and it makes these molecules undergo some changes. You could potentially break bonds where you have, say, an unpaired electron on the carbon, that's what that dot is, or say a lone pair on the carbon. This carbon atom only has 6 total electrons in its valence. These are very unstable bits of a molecule. And so these are very unstable bits of a molecule. Functionally, what you create are intermediates of the overall process. So that's what you kind of jump into the intermediates. That's what gets the reaction going. All of a sudden, you're past that sort of initial part where you have the first couple steps are done. You have these intermediates that are now present. They can start to drive the reaction and get it going. You release heat. That makes it easier for other C3H8 molecules to fall apart and get this thing moving. You get this very fast chain reaction that self-propagates.
All right, first video down. We've already found our first question for participation 918. One's due Friday night. This is going to be the final set of videos for the week. We've got our week 4 homework due Saturday and the Crystal Violet Post Lab due Sunday. This will be the end of chapter 12. Next week, we will do our first test, exam 1. If you have any questions about anything, let me know. Don't hesitate to reach out. If you want to meet to talk about the exam or anything that's going to be on it, happy to do that. Otherwise, enjoy the rest of the videos. Bye-bye.